Hi everyone, in this video I'm going to address the following question. If you have a convergence sequence of random variables, can you swap the limit of this sequence with the expectation? And we're going to give the first answer to this question here. The theorem we're looking at here is called monotone convergence theorem. Monotone convergence theorem. Okay, and I'm going to tell you about this theorem in the probabilistic language, but if you've seen a measure theory unit, or if you go to a measure theory unit, you'll see a similar proof in terms of functions. Okay, page 1. So the theorem says the following. It has two parts. Part 1a, let xn, well x1, x2 and so on, be a sequence of random variables. Okay, and the assumptions are the following, such that so assumptions are the following. The first assumption is that there exists a random variable y such that for every n we have xn bigger than or equal to y, and this y has a kind of an integrability probability, namely the expectation of y exists and it's not negative infinite. Okay, so remember that a random variable can have different cases. It might not have an expectation, it might have an expectation, and that could be minus infinity or positive infinity, or it could be finite. We don't want y not to have an expectation, and we also don't want y to have minus infinity as an expectation. Okay, so that's the first condition. The second condition is that xn is non-decreasing and converges to another random variable x. Okay, so xn is non-decreasing, and this is a short notation for xn to be non-decreasing and converging as n goes to infinity to yet another random variable x. In that case, so these are the assumptions. In that case, then the expectations of xn to be more precise, will converge in an increasing fashion to the expectation of this limiting variable x. In other words, this is a theorem about swapping limits and expectations. X is actually, I forgot to say, it's enough to have this almost surely, so with probability 1. Okay, in fact. So x is the limit of the xn's, an increasing monotone limit of the xn's, and the limit of the expectation of the xn's is the same as the expectation of the limit of the xn's if these conditions are satisfied. So this is part A of the theorem. Part B of the theorem is very similar. Part B, so I'm going to almost repeat the assumptions, x1, x2 and so on. Let these be random variables such that, and what I'm going to do here is pretty much the same thing as before. There exists a y such that for every n, xn is actually smaller than or equal, so it's bounded from above by y, and the expectation of y exists and it's not positive infinity. Let's furthermore suppose that the xn's converge to x in a decreasing fashion. Let me change paper here. So I'm also going to assume that the xn's converge to x, this time in a decreasing fashion. Okay. Page 2, you don't see that, but that's fine. So let's also assume, assumption 2, that the xn's converge to x in a decreasing fashion. So this is short notation for two things. Xn's are decreasing for every omega. They are functions of omega. They are decreasing and their limit is x. And in that case, you can again, if this is happening for every omega or almost every omega, in that case, the statement is the same. The expectation of the xn's will converge in a decreasing fashion to the expectation of x. Okay, this is statement B. So if you now compare statement A and statement B, then it's pretty much the same thing, except one is for increasing sequences, the other is for decreasing sequences. Okay, so let's prove this. And for the proof, I am first of all changing paper again, because I need a lot of space for this one. And the starting point is a good picture and some stuff we had before on the lectures. So the starting point is the following. I'm going to prove, first of all, let me put back this paper on here first, because let's just put this much here for the proof. Step 1, if you want. We're going to do only case A. Case B is very similar. And I'm going to assume that this bounding random variable is just 0. So what am I talking about? Here's the statement again. Let x be random variable such that there is this bounding random variable so that all the x's are bounded from below by y, which has a non-negative infinite expectation. Okay, that was the assumption. Now, in this special case, I'm proving for the first round, I'm going to assume that this bounding variable y is 0. In other words, the assumptions are that xn converges to x in an increasing fashion, and the xn's are simply non-negative. Okay, so these are the assumptions. Under these assumptions, I'm going to show you how to prove the theorem, and then from here it's going to be an easy generalization for the general case of part A. Okay, so the xn's are non-negative. Of course, the limiting x's are non-negative as well. In fact, it's enough to have this almost surely, but we're not, okay, we'll see how that comes in the picture. All right, and the point is that this is a sequence of random variables for every n, and if you remember on the previous lectures, what we said is that the xn for every, actually I'm going to use k here, no, sorry, I'm going to use n. For every n, we have this random variable xn, will have a sequence xnk of simple random variables that will converge in an increasing fashion to xn as k goes to infinity, and again these guys here are simple. Okay, this was a statement we had before. I didn't prove this before. It just comes from measure theory. Simple random variable means that it's piecewise constant, so it's some indicators of some sets times some values, and you have a finite number of these. You have a sequence of simple random variables that converges in an increasing fashion to every member of that sequence. For every n, we have this convergence. And that's what I'm going to draw in the next page, and this is going to be the starting point. Okay, so this is page 3. And so the picture is the following. So we have the sequence x1, which is smaller than or equal than x2, smaller than or equal to x3. I'm going to draw a few of these, smaller than or equal to x4, smaller than or equal to x5, and so on and so on. And they converge in an increasing fashion to the limiting random variable x, at least for a probability 1 set of omegas. Okay, so this sequence converges there. And now what I'm going to do is that I'm going to put here this other sequence for every n in this row. I'm going to put down an x1, an x1, 1, which is less than or equal than x1 of 2, which is less than or equal to x1 of 3, and so on and so on. They converge in an increasing fashion to the first member of this black sequence. Okay? And now I'm going to do the same for all of them. So these simple random, so these are going to be simple. These simple random variables exist for all n. So I'm doing n equals to 2 now. It will take a while, but I need a large picture for what's coming. x3 of 1 is equal to x3 of 2 is equal to x3 of 3, and so on. Okay, x4 1 is equal to x4 2, x4 3, and so on. x1 1 is equal to x5 2 is equal to x5 3, and so on. Okay. And now the main object of interest is going to be a random variable Zn. So I'm going to put that here. Zn, that is going to be the maximum, that is going to be the maximum of the x j n's as j goes between 1 and n. The largest of the xj n's as j goes between 1 and n. So what is z1? Well, z1 simply has n equals to 1. J has to be 1 as well, because it's the maximum between 1 and 1. So that's 1. So z1 is clearly x11. This is z1. What is z2? z2 is going to look at the second level of this picture, the second row of this table, and picks up the largest of the first and the second entry of these. So z2 is going to the maximum, the largest of these two people. That's what z2 is going to pick, so the largest of these two. What is z3? z3 is going to be the largest of the third level of these simple functions. Okay, so z3 is going to be the largest out of these three guys. All right, and now the xij, so all this table was simple piecewise constant for a finite number of different values. Okay, and that implies, of course, that the largest of simple random variables is still simple, it's still piecewise constant, it still can change values on a finite number of different sets. So it follows that Zn is also simple. Okay, that's the starting point, that's the main picture to keep in mind. I'm going to bring this picture back a couple of times. And so now let's make a few observations based on this picture. Let's make a few observations based on this picture. Oops, I need to adjust my setup here. Okay. So, the first observation is that, so let me change colors back here. The first observation is going to be that xn, which was the original sequence we were looking at, this is page 4, so xn is larger than or equal to Zn. That's my first observation, and let's just quickly verify that from the picture. So here is the picture again, and I want to claim that x3 is larger than or equal to z3. Okay, x3 is larger than or equal to z3, which is the maximum of these three guys. Why is that? Suppose this is the maximum, this is the largest of these three. Now if I start going up, I can only increase my value, and if I start going to the right to reach x3, again I can only increase my value. So x3 is largest than the highest value here. In other words, x3 is larger than z3, and this is true for each of these guys. And now I see that my notation was not exactly perfect. Sorry, I should have put this index down here. I should have put this index down here to be consistent with the previous page. Okay, so again, this Zn here is smaller than or equal than xn. x3 is larger than or equal than z3. That's the first observation. Okay. Now the second observation is just by the definition of Zn. Zn is of course larger than all of the xk's. Zn is of course larger than or equal to any of the xj's, or if let's use k, and that's again a very simple consequence of the definition of Zn. If you look how Zn was defined, Zn was defined as the largest of the xjn's, j between 1 and n, and therefore, at least when I fix k between 1 and n, then Zn is larger than or equal than xk of n. So this is again, this is true for any k between 1 and n. That's my second observation. Okay? Now, the third observation is the following, is that Zn is also larger than or equal to Zn minus 1. Why is that true? So what this claims, as an example, is that Z3 is larger than or equal to Z2. What was Z2? Z2 is the largest of these two guys. For example, it might be the first one. Z3 is the largest of those three guys. For example, it might be this middle one. So if I go from the largest of the second row up one row, that will be larger or equal than the largest of the second row. And now if I maximize again over these three entries, or over whatever number of entries I have, then I again can only increase my value. So Z3, if this is the maximum element in this row among these three guys, if this is Z3 and this is Z2, then I increase the value this way and then maximize across all these three people. So that's how I'm getting to something larger than in the previous row, and that's why Zn is larger than or equal to Zn minus 1. Now, if you have an increasing or at least non-decreasing sequence, it follows that, so let's change colors. It follows, so an observation following up from this one is that Zn's increase and any increasing sequence converges to some limit Z. Some limit Z. Okay, so there we do have a limit of these Zn random variables. Now, I'm going to take a limit of the first two lines. I'm going to take a limit of the first two lines. If I take a limit of the first line, if I look at this inequality and take n to infinity, I know that xn's converge because that was my assumption. Everything I say here is almost sure, so the probability 1 set. Xn converges to x, and Zn, I just concluded that it converges to z, and therefore in the limit I still have x larger than or equal to z. Okay. On the other hand, if I look at the second line, Zn converges to z. So if I take a limit as n goes to infinity, for every fixed k, Zn will converge to z, and that will be greater than or equal in the limit than when I take n to infinity. For x and k, I actually end up with xk. Okay. Why can I do that? Because I'm fixing a k and I'm taking a limit as n goes to infinity. Eventually n will become larger than k, in which case this inequality kicks in and my limiting inequality actually holds. So that's nice, because now if I combine these two, then from these two I read that xk bounds z from below, but x bounds the same z from above. So now if I take a limit in k, then I conclude, if I take a limit in k, then I conclude that z must be the same as x. Okay? So z must be the same as x. Now what was the point of this whole construction? So let me come back to the previous page and look at this whole construction. So I had my sequence of random variables that converges up to x. Okay? I have simple random variables, the brown ones, which converge to each of these sequence. I take a maximum of a finite number of them, so Zn is still simple. And what I now concluded is that the Zn's converge to a limit, and that limit is actually the same as my random variable. So I produced my limiting random variable x as a monotone limit of simple random variables, because it's very important that these guys here are simple, which the original xn sequence was not, or not necessarily. Okay? So I have a monotone limit of simple random variables, and then the way we defined expectations before implies that in this case I know how to define the expectation of Zn's, I know how to define the expectation of Z, and the definition included that any monotone sequence of simple random variables will have their mean converging to the same limit, and that's how I define the expectation of Z. So it follows that the expectation of x, which is the same as the expectation of Z, by this observation here, and then because it's simple, it is going to be the same as the limit of the expectation of Zn. So the whole idea is that because the Zn's are simple, the definition of the expectation of Z is the limit as n goes to infinity of the expectations of the Zn's. Okay? So that's the main idea, and we're not yet finished because the expectation of the Zn is smaller than or equal than the expectation of the Xn. So I can add here the limit of the expectation of Xn. Why is this true? Why is this true? Well, that's simply coming from that inequality here. Xn is bounding from above the Zn, so the expectation of Zn is bounded from above by the expectation of Xn, and so if we have these limits, which we do, then the inequality must hold true. Okay. On the other hand, we also know that the xn is smaller than or equal than the xn plus 1, because we started with the sequence x to be monotone non-decreasing, and so on, smaller than or equal to x. So it follows from this line here, then all of the xn's, each of the xn's have a smaller than or equal expectation. Each of the xn's have a smaller than or equal expectation than x itself. Okay? Which of course holds true in the limit. So the limit of the exn's, which exists by monotonicity of course, is smaller than or equal than e of x. All we have to do now is to look together these two inequalities. E of x is less than or equal to the limit of the exn's, but it's also larger than or equal than the limit of the exn's. So it follows that these two are equal. So the limit of the exn's, let me change page. This is 5. So the limit of the exns, is the same as E of x. And that's exactly what we wanted to do, at least for part A. Okay? Or, well, part A and also the assumptions we had. Let me come back to this page here, which we started with, the proof, if y equals to 0. Part A, which is the increasing case, if y equals to 0. Okay? What do we do if y is non-zero? So from here it's just going to be some simple arguments. If y is non-zero in general, but still, of course, we have to assume that y has a non-negative infinity expectation, not equal negative infinity. So in that case, what you need to do is consider xn minus y instead of xn. Okay, xn minus y is going to be a non-negative random variable because xn is assumed to be larger than y, so xn minus y will be non-negative. Its expectation is of course not negative infinity, and if we repeat every argument for that, then that shows the statement for part A. And part B is very similar. I'm not going to do that again. It's exactly the same statement reversed. That's the end of the proof. Thank you.